afternoon, everyone. Allow me to introduce myself. I'm Sujata on behalf of ITP Media Group, Manufacturing Today, and Husky Injection Molding Systems. I welcome you all for today's webinar on advancements in hot runner and controller technology for medical and complex molding. In this webinar, hot runner experts at Husky will focus on recent hot runner and control technology advancements that provide higher level processing capabilities to molders, but reduce production risk and increase capacity. Allow me to introduce Manufacturing Today to you. Manufacturing Today is the flagship brand of ITP Group, which is headquartered in Dubai and is India's leading industry magazine, which focuses on people, processes, and technologies for SME and large manufacturing companies. It's a one-stop shop for the latest news and views on India's vibrant manufacturing sector, from operations to supply chain management and product development to innovation and advancements in technology. The magazine is peppered with in-depth articles, site visits, and case studies, offering insights into what keeps large and medium-scale organizations in this space ticking. Manufacturing Today reaches key decision makers and is circulated across the country with the content that contains insights and updates, interviews, analysis, and well-directed research. Our partner today for today's webinar is Husky Injection Molding Systems and world leader in injection molding systems. Husky Technologies is a leading industry technology supplier to the plastic processing community. The company designs, manufactures, and services the industry's most comprehensive range of injection molding equipment, including machines molding, hot runners, auxiliaries, and integrated systems. Its value-added services include preform development, part design, factory planning, customer training, system integration, and complete asset management. Customers use Husky equipment and services to produce a wide range of products for beverage and food packaging, medical, home care, beauty and personal care, automotive, and consumer electronic markets. 4,000 people worldwide, Husky supports customers in over 100 countries. Its main manufacturing facilities are located in Canada, United States, Luxembourg, Austria, Switzerland, China, India, and Czech Republic. With this, I would like to introduce our speaker for today, Derek Hennebeck, who is a product manager, hot runners for Husky Technologies. Derek is currently responsible for new product launches, specialty applications, and product portfolio management. With over 20 years of experience in the manufacturing and plastic application, he specializes in hot runner technology and injection molding. We also have Rajan Kasi, who is the Vice President, South Asia Hot Runners and Controllers, Husky Injection Molding System. Rajan is an accomplished engineer with over 25 years of experience in the mold, tooling, and processing industry. He has held a variety of roles supporting customers, adding value to clients' manufacturing processes in several countries. Rajan holds a master's degree in engineering from University of South Australia. Over to you, Derek, for the presentation. Thank you.
Hello, everybody, and thank you for having me today. I'll start by introducing myself. My name is Derek Hennebeek, and I am the product manager for Hot Runners here at Husky. I'm responsible for new product launches, specialty applications, and product portfolio management. I live on the East Coast of the United States, and I've been in the industry for about 20 years, 12 of them with Husky. My contact information is shown here, but I will give it again at the end of the webinar. The purpose of today's webinar is to improve understanding of how and why hot runners play such an important part in the injection molding process for the medical industry. First, I will introduce Husky Technologies and summarize the experience we bring to the market and the industry. Second, a quick explanation of medical molding. Third, a brief summary of hot runners and the benefits they bring to injection molding. After that, an explanation of various gating technologies, especially valve gates, and why they are best suited for medical manufacturing. And finally, we will go over some other technologies that are a great fit for medical injection molding applications. Now, I will introduce Husky Technologies, as in who we are and what we do. We are an industry-leading company who manufactures injection molding equipment and provide services around the world. We design and supply hot runners and temperature controllers for mold makers, converters, and brand owners. We utilize standardized engineering and manufacturing to ensure consistent product and performance anywhere in the world. All of this drives our goal of being the highest quality provider of the world's most reliable hot runners. We are a global company with our headquarters in Canada and manufacturing in the United States, Luxembourg, Switzerland, the Czech Republic, India, and China. We have additional tech centers and sales offices in various locations of the world. This infrastructure allows us to meet the unique needs of our customers worldwide, delivering global solutions executed at the local level to provide shorter lead times, responsive service, and dedicated sales support. When it comes to the design and manufacture of various melt delivery and hot runner solutions, we serve a variety of market segments and work with several different applications. Each of these has their own unique solution when it comes to thermal management and melt delivery due to each application's specific needs, starting with single drops, which function as a machine nozzle extension for prototyping, low cavitation hot runners, typically used for parts with intricate mold actions, such as sharp carriers and device housings, and high cavitation hot runners for molds built to support extremely high output rates, such as blood collection tubes, and stack molds for parts with short draw height and large machines to take advantage of projected area and maximize production. Beyond typical hot runners with hot tips or valve gates, Husky also designs and builds hot runners for specialty applications like angled drops for large parts with highly contoured part geometries, drop-in systems for simplified plate design, side gates for narrow, long draw parts like pipettes or lure locks, and specialized melt delivery systems for intricate and finely tuned injection control. We also design and build controllers under our ALTANIUM brand for hot runner temperature control, valve stem motion and timing control, and mold action servo control. Husky also provides services to support its hot runners and ALTANIUM controllers. These include hot runner refurbishment, on-site hot runner training and repair, call desk support for drawing requests, reference information, and spare parts, and e-commerce services for immediate quote and expedited delivery of single drop and low cavitation systems. Finally, in addition to standalone hot runner technologies and equipment, we also offer a full turnkey system approach. We do this for specific markets, including medical, where we design and build a machine, mold, hot runner, and handling system tailored to your production requirements. As you can see, Husky provides a lot of technical diversity. We offer simple stuff, complex melt delivery, and decades of experience focusing on all kinds of applications. So come to us anytime with your questions. Now that we've talked about ourselves, our products, and our services, let's talk about medical applications and how they relate. There is a lot of focus on medical manufacturing. We saw this with the recent COVID-19 pandemic, where it was important to get more parts, devices, and components into the hands of the people that needed them. Though priorities have shifted, we're all still very aware of the attention on the global supply chain. Our global population is increasing, and so is the GDP and global health expenditure. This means more money is spent on medical needs than ever. The average age of our global population is also increasing. Older people typically need more medical care through services and devices, representing an ever-growing target market. Lifestyle and changing medical conditions also drive change in the medical industry. The increased occurrence of chronic conditions like diabetes in the United States has driven the need for more effective devices and drug delivery systems. Initially, medical injection molding seems the same as conventional injection molding for any other market or application. We go through several validation sequences to fill the cavity, pack it out, eject parts, and repeat, all the while ensuring that those parts are in spec. But it's much more than that. Fits and functions of these parts and their assemblies are very precise, and variation is undesirable. This is because there is so much risk and liability tied to each part and its function. Control is also important to ensure the same actions can be performed to get the same result every time, not just by parts and devices, but by the injection molding process. Finally, contamination is unacceptable. This is not just with resin integrity or purity, but by contaminating the process with changes in settings and conditions. Because of these needs, this is why we have so many different and complex hot runner and melt delivery system solutions. Now that we've established the criteria and needs of medical molding, let's talk about how hot runners help to meet those needs. Before getting into the complexities, it's important that we all understand the basics. A mold's mission is to make a profit by making a part. To make that happen, it needs to accomplish 5 things. It needs to deliver molten resin to the cavity, allow air to leave the cavity when displaced by the molten resin, give that molten resin a shape, remove heat from the molten resin so it solidifies to a dimensionally stable product, and allow access to removing the resulting solid part. The runner is our focus today, which is what we call a melt delivery system. This is the road the resin takes from the injection molding machine's barrel to the mold's cavity, where the part gets its shape. When this is done by machining a specific channel in the mold and removing the frozen plastic that fills the channel every molding cycle, this is called a cold runner. These are frequently experienced by people who assemble models or toys because they hold all the pieces together. While easy to incorporate into the mold design, these cold runners must be removed from the mold each cycle. They sometimes must be removed manually from the part also. These cold runners also have the thickest cross-section of all of the parts in the mold. This adds time to the molding cycle. Because more time is needed to remove the heat from the runner so it can cool enough to handle without sticking to the molded product or burning the operator. Finally, these cold runners must be handled, not just by removing it from the part, but by transferring it someplace else. In some cases, these can be processed into regrind, but in other cases, they can only be thrown away. Either way, equipment or people must manage and move that material. Many medical applications require the use of virgin resin from a variation, tolerance, and purity or decreased risk of contamination standpoint. As an example, let's look at a 64 cavity mold for a 2-gram part. Its cold runner weighs 192 grams, assuming all parts are perfect and meet specification, and a 100% virgin material requirement. 60% of that used material is scrapped or discarded every cycle. But by direct gating these parts, that waste and handling effort is eliminated. Removing that thick-walled cold runner also enables a faster cycle time to increase output. A mold with a hot runner certainly has a higher entry cost to invest in the asset. Cold runner handling with its associated costs and risks are difficult to quantify, but the savings quickly add up when virgin material is the requirement. Faster cycle times are very easy to recognize and to quantify, but not only is the part quality improved, but in several ways. Variation can be decreased if regrind content is minimized. More gate location options can decrease cavity pressure for an optimal fill profile. Especially helpful is improvement to the gate quality and its reliability, which we'll cover in a few slides. If you have any questions or interest in exploring the conversion of an existing mold to use a hot runner, we have tools to review and quantify all of these points and investments. There are several gate and control choices available when it comes to hot runners. We'll talk about those now and how they relate to medical molding. The gate is the boundary between the melt delivery system and the cavity. It's usually a restriction smaller than the part's nominal wall thickness. This ensures the gate freezes before the material in the cavity. This rings true with what is often the classic example of the hot runner, the thermal gate. This is also sometimes called an open or hot tip gate. A small probe of highly conductive material is suspended in the melt stream and transfers heat as close as possible to the gate. At the end of the cycle, the material cools just enough to form a skin to prevent drooling in the cavity when the parts eject. This frozen layer is so thin that on the next cycle, it pops to allow melt to fill the cavity again. And it's called a thermal gate because it's very much dependent on thermal conditions. The other gating method is mechanically controlled. This form of gate control is called valve gating. Rather than rely on the thermal properties of the mold design and the resin to close and control the gate, a mechanical interface is used to open and control that gate, acting as part of the cavity when closed. Each of these has advantages and disadvantages. Thermal gating uses simple construction and no moving parts. This makes for a lower starting cost, but this simplicity also limits its applications. The interplay between cooling and heat profile make it very specific for resin and sometimes even its grades. Resin properties can limit capability and the process window. Gate quality expectation is very specific to a combination of gate diameters and those material grades. Meanwhile, valve gating may have a higher starting cost, but it also affords several advantages. Gate quality is determined mechanically, removing its influence from the material and the dimensions. Larger gates are also possible, which give less stress in the part and reduce temperature rise at fill, both enabling faster cycle time. This decreased thermal sensitivity allows greater resin capability, better balance, and a wider operating window, all of which are ideal for medical molding and its need for decreased variation, both cavity to cavity and shot to shot. Here's an illustration of gate quality expectation for each gating technology with the same resin. On the left, we see a thermal gate and a close-up of its gate quality. On the right, we see a close-up of a gate from a valve-gated hot runner. We see the valve gate has near ejector pin quality when it comes to the gate finish on the part, thanks to the mechanical fits and controls. This does not mean good gate quality or consistency is impossible with a thermal gate. It's just much more dependent on factors like process, part design, tooling, conditions, and the resin. Gate quality is very important for medical applications because it's all about avoiding risk. Gate quality can dictate the functionality of a device, like housing, a pipette, or a drug delivery system. Contamination is also a concern, in the case of preventing a surgical glove tear. In other components, like catheters, poor gate quality can be very noticeable very quickly. Since we've established mechanical gating is the best option for gate control for medical molding, we'll talk about the various ways available to manage gate quality and control the process. Valve gating has two different shutoff types or interfaces between the valve stem and the gate. These are a conical interface, sometimes called a taper shutoff, and a cylindrical interface, sometimes called a plunger shutoff. A conical interface provides very good and manageable gate quality. It features direct contact between the conical edge of the valve stem and the gate steel. There is a medium machining tolerance for the gate due to necessary contact. But because of this contact, there is a potential risk to flex and crack the gate with fatigue failure over time, especially if the stem force is very high. This is why it's important to follow the tolerances to maintain contact for gate quality, but to minimize load. The other interface is between the stem and the gate, which is the cylindrical interface. This gives the best possible gate quality, but it also requires the tightest tolerances to make that happen. Gate attributes like roundness and straightness are very important. Because of this very tight clearance, it's highly unlikely to crack the gate from stem loading, and a very long gate life or gate quality life is possible. We've talked about the two different ways to separate the melt from the cavity, but we need a vehicle with which to drive that shutoff. There are two styles of vehicle: series, where each valve stem is physically driven by an individual actuator, or parallel, where a group of valve stems are driven by a single actuator. Individual actuation has been common in the industry since the release of valve gating. Each shutoff is driven by its own actuator and its media. The benefits are better balance than a thermal gate due to mechanical control. Maintenance is also simple and intuitive. If a cavity has a problem, the actuator can be investigated. But since each cavity is controlled by an individual actuator, these can sometimes limit cavity spacing due to each actuator's size. Plate actuation is a more recent development in the past dozen or so years, where all valve stems or groups of valve stems are tied to a single actuation plate. You can imagine this as an ejector plate inside the hot runner, driving all the valve stems open and closed. This plate itself is moved by actuators, depending on the force required and the media used to control its movement. Because movement is controlled by a plate, cavity spacing can be pushed much closer together. This is because it's not limited by the actuator size. The unified movement of those valve stems, or gate control, also affords the best control over cavity balance and cycle variation, since the open and the close order of each valve stem is the same every single time. Finally, there are three different methods to control that actuation. This is what generates the force for moving the valve stems to open and to close those gates. These are pneumatics, or compressed air, electronics, or servo motors, and hydraulics, or pumped fluid. Each media has its advantages and disadvantages, typically with force, positioning accuracy, and speed. Other things to consider are response, maintenance interval, and movement variation. Pneumatics are very popular, where the circuit design is very simple and it has low starting costs. Loads and closing forces are very dependent on equipment and component design, such as piston diameters and air compressors. Loads are either off or on and depend on components to determine physical position. These types of systems are easy to maintain by monitoring performance and changing seals as needed. But those seals wear over time, and the cycle count can introduce some variation in that seal condition over time. Electronic or servo drive is becoming very popular. This is a very clean way to move those components, whether it's valve stems or other mold actions. It has a high initial cost, but the maintenance is very simple. These systems offer the best control. Open and close timing can follow specific settings, so the first cycle can move with the same timing and speed of the 10 millionth cycle. Because these drives require a controller, traceability and record keeping is often a feature available for tracking performance, all of which are extremely valuable to medical molders. Finally, hydraulics offer very high loads and closing forces for the size of the units available. But movement is either off or on. It's moving or stationary. They can be moderately complex when it comes to pump management, but if there is a leak or a line failure, it can be very difficult to manage and take a very long time to repair. In the next few slides, we'll talk about some common gate quality defects. Great gate quality is never the result of just one factor. This depends on the proper use of the combination of several factors. Some of the steps and checks that I'll give here are not resolutions or fixes, but indicators of influence or troubleshooting tools to show what may need consideration to change the outcome. Posting is a defect description used when a small mass of material protrudes from the gate location and it matches the gate geometry. It looks like a post that sticks up off of the part. This is when resin in the gate orifice freezes or sets up before the valve stem fully closes. If this is on an unvalidated tool, it's best to check the gate orifice while the mold is open. With the stems fully forward and in the hot condition, the stems should slightly protrude through the gate. This ensures the nozzle and the stem length match the cavity. If this doesn't check out, nozzle components might be mismatched or for the cavity, or there could be a blockage preventing the valve stem from moving fully forward to properly close the gate. If this is a mold trial, you can ensure fill and hold are not overpacking the cavity by minimizing the hold time. The nozzle or mold temperature might be too low, causing the resin to freeze too quickly. This is important to confirm because closing valve stems on frozen resin, even soft resins, can very quickly damage gates and stems, requiring expensive replacement or timely repair. It can also mean the stem closing force is inadequate. With pneumatic actuation, it's important to use the recommended air pressures from your hot runner supplier. If this is on a validated part, confirm that you still have adequate air pressure. Another gate quality defect can be called crown flash. This is when a small ring of flash at the perimeter of the gate orifice. This can indicate a clearance or an increased clearance between the valve stem and the gate orifice. So it's best to confirm the stem diameter and the gate diameter to make sure that they match. This should not be done with gauge pins and calipers, but with a CMM at 3 planes and at least 30 points per plane. This is to ensure the gate is not tapered or out of round. Crown flash can also be the result of the molded material. Some resins like polypropylene or polyethylene are very ductile or stretchy. If the part is overpacked, material may have packed into the clearance area between the gate and the valve stem. That ductile material might also still be hot at ejection. These factors can be confirmed by significantly reducing hold time, significantly increasing cooling time, or significantly decreasing the mold or the cooling temperature. Each of these settings should be changed, and the results should be observed and recorded as they indicate different influences beyond the gate clearance. A third gate quality defect is the hot gate. In this scenario, a deformation, ripple, or a tear can appear at the face of the stem or just outside the gate. This indicates that sufficient heat has not yet been removed from the part near the gate. This can be investigated with a number of different tactics to extend the cooling, such as increasing cycle time or reducing the process temperatures. In some cases, exaggerated settings may be needed to confirm these conditions. If these prove successful, the cooling strength at the gate should be increased to remove the heat from the part more quickly. This can be done by increasing the valve stem's contact land with the gate or through other process changes. The question occasionally comes up, what affects the gate quality? This is always a difficult answer with a lot of details because it's the combined influence and result of so many things. While every mold and part are very different from each other, a strong foundation is in the machining of those gates to make sure that they're very round and very straight. This gives the smallest clearance possible, which gives the greatest success. However, this can be quickly undone with damaged components. It doesn't take many cycles of closing on cold material to damage those stems and gates. They're very, very small parts and they're managing very high forces. Valve stem shutoffs are small parts that see very high loads at high speeds. And finally, the application itself always has an influence. Crystalline resins like nylon process differently from amorphous resins like polycarbonate. Each of these has very different properties from polypropylene, whose glass transition temperature is below zero in both Celsius and Fahrenheit. Different improvements can be made with different degrees of change to process settings and the mold cooling. Finally, I'll talk about various offerings from Husky and how they meet the medical market needs. Extended gate quality is extremely beneficial. This means reduced downtime and longer production between maintenance cycles. This is achieved through our UltraHelix nozzle and is available in several nozzle sizes. Its valve stem is precisely aligned with the gate to minimize contact, which can result in gate wear. The valve stem is guided and supported within the UltraHelix tip throughout the entire molding cycle, which provides a very precise stem-to-gate fit throughout the entire molding cycle. This allows for gate life that lasts for millions of cycles, much longer than any other valve gate available on the market today. An enhancement to that extended gate quality is parallel or synchronized valve stem control. This is accomplished with our ULTRASYNC plate actuation technology, which gives 100% synchronization of the valve stems managed by electric, pneumatic, or hydraulic drive media. Electric control gives the best consistency, traceability, and control cycle after cycle, which is ideal for medical, technical, and high precision small parts. Only limited maintenance is necessary with any of our plate actuated hot runners. We recently announced the release of our UltraMelt hot runner construction. This is ideal for medical applications with its non-reactive melt path and minimized thermal variation, all utilized to minimize the risk of degraded or discolored resin, which is so important to the medical market today. With our ULTRASHOT technology system, molders can produce parts at scale previously impossible to do with conventional injection molding technology. This utilizes the plasticating unit of the conventional injection molding machine to feed molten resin to servo-driven injectors, which directly feed specific groups of cavities. This moves the injection control much closer to the cavity, reducing residence time, decreasing variation, and increasing control for parts with very low weights. This makes it possible to increase productivity with a reduced work cell footprint by scaling up those smaller molds. This capability also improves part quality, design freedom, and resin properties compared to conventional injection molding. This empowers new part designs that increase functionality, improve cost efficiency, and display creativity without being limited by the injection molding process. This even allows the possibility to reduce or eliminate subsequent manufacturing steps. In the example on the right, a conventional injection molding machine could only fill the cavity so far before becoming pressure limited. This is not surprising since the application was less than 0.3 grams with an L/T ratio of 140. When fitted with an ULTRASHOT melt delivery system, we achieved a 40,000 psi fill pressure to push the flow front much, much further. This illustrates some of ULTRASHOT's capability when it comes to lightweighting or replacing processes with injection molded geometry. In another test, we tracked flow front arrival in several mold cavities with temperature sensors and compared a conventional hot runner's construction to an ULTRASHOT injection system. This combination of closer injection control and increased response gave a much tighter window for fill control. This shows a direct display of the ULTRASHOT's increased capability when it comes to cavity balance or minimized variation. This is so important for high cavitation molds making small parts, where process and design wield so much more influence over the molded results. Finally, in an ULTRASHOT case study, we were presented with a part so challenging to fill and manage, the molder was limited to work cells using only 2 cavity molds. Due to part geometry, the scrap rate on these molds was very high, well into the double digits. Quality, consistency, and repeatability were a major challenge. To meet increasing production demand and the increased demand created by COVID, a major investment of additional machines, molds, and floor space was required, but difficult to justify. They really needed to increase work cell output, not just with an improvement in production quality, but by scaling up to a higher mold cavitation. ULTRASHOT was able to increase the capacity to an 8-cavity molding cell. This compressed production to much less floor space. Major improvements were made to part quality, not just shot to shot, but also cavity to cavity. This decreased the scrap rate significantly, making huge gains in reliability and production output. Temperature control provides a significant influence to the operation of a hot runner for successful medical molding. Our ALTANIUM controllers employ ART, or active reasoning technology, to account for each element of the control process. This is because temperature control is determined by input signal quality, control algorithm precision, and power output speed and uniformity. This is a continuous loop process which constantly communicates between the controller and the mold to ensure extremely accurate temperature control. Our controllers also allow some unique and helpful features. One of these features stood out in a recent case study. We had a customer molding a 4.5 gram polycarbonate auto injector housing. A challenge they saw was with cycle interruption. When the cycle was interrupted and production stopped, they were unable to promptly answer the machine alarm and restart production. This prolonged exposure to heat for the melt would degrade the material. This would require a prolonged purge of the machine and the hot runner, and a cleaning procedure for the molding cores. By using our ALTANIUM feature for remote standby, the temperature settings of the hot runner were immediately banked down or decreased when a cycle interruption was communicated by the machine exceeding a specific time window. Thanks to this temperature reduction, the melt kept its integrity much longer. This significantly decreased the issue occurrence rate, saving more than $25,000 a year in cleaning costs, and recovered at least 4 weeks of production capacity every year. This standby feature is incredibly helpful. Cycle interruptions are unwelcome, but we recognize that they happen, and this is a feature that's very helpful for minimizing risk and maximizing uptime for medical molding. This requires communication directly between the injection molding machine and the temperature controller, but it's easy to configure for the problems it helps to avoid. That concludes our webinar on hot runner and controller advancements for medical molding. We have some time to take questions, and if you have a question sometime after the webinar, you can reach out to me directly anytime at the contact information shown below. Even if those questions don't involve medical molding, but what Husky can do for you when delivering melt to the cavity, feel free to reach out. Thank you, everybody, for your time today.
Thank you, Derek. Thank you very much for your insightful presentations. We have some questions. So the first question is, are there any limitations or design consideration when specifying the VG hot runner system?
Yeah, so VG is short for valve gate. So some of the considerations or limits with a valve gate system is it typically has a higher starting cost or a higher price to purchase compared to a hot tip or a thermal gated system. They also have a bit thicker of a shut height or a greater effect on mold thickness, just because it needs to account for the space needed for the actuation. And sometimes there is a little bit of a limit on the spacing between the cavities. One way that can be circumvented or solved is by using a plate actuation, just because by putting all of the valve pins or the valve stems in a single actuating piece into a single plate, that helps to bring things more close together compared to an individual actuated valve gate. And then finally, there just needs to be an interface from the injection molding machine to make sure that the cycle information is communicated to the hot runner, so that the valve gates can be controlled at a specific time, open and close. So a little more complexity, a little more cost, but as we mentioned earlier in the webinar, all worth it.
We have another question. Have there been any recent application or part design trends that have created new challenges for HR performance?
The way the industry is going is we want to, well, not we, and it's not right to say they, but the industry is really going toward making more parts in smaller molds and making smaller parts in smaller molds. So 20 years ago, it was not very common to see a part that was less than 1 gram. But now we are seeing more and more parts that are less than 1 gram in part weight or part size, even more so half a gram or a quarter of a gram. There are very, very small parts out there, and they are becoming much more common for direct gating. It's very easy to make those parts with a cold runner. It's just because of space, but to direct gate those parts to save the material and to save the cycle time is just becoming more common. We're also seeing more parts that have smaller and thinner features to those parts, and those smaller and thinner features also have finer tolerances. So that becomes much more important. It becomes very important for good mold build quality. It also becomes very important for good process control. And that means more consistent hot runners, and sometimes very sophisticated hot runner technology to support that, to support those very fine features and to support that very strict requirement to meet tolerances and specification.
The next question is, what is your experience with PC applications, especially for high-end medical parts?
Husky has very deep and extensive experience when it comes to medical parts and to high-end parts, especially polycarbonate parts. So as far as, you know, both of those, I was asked that question the other day by somebody in our sales team, and I did some checking. We build about, I want to say it's about 1,000 hot runners a year for polycarbonate applications. And that comes out to about 4,000 to 4,500 individual nozzles or individual cavities that we're working to supply melt to every year. So year over year, we're building 1,000 hot runners just for polycarbonate. That doesn't consider any other material like polypropylene or PET or PEEK or PSU, but that's just polycarbonate, and that's 4,000 to 4,500 nozzles or drops that we work with.
So what experience do you have with high temperature or corrosive resin?
We have a lot of experience with those also. So much that we have a common approach to those applications, to both the high temperature and to those corrosive applications. And sometimes those two application styles overlap because some of those high temperature materials become corrosive when they degrade. But when it comes to corrosive materials or corrosive applications, we will typically build a full stainless steel hot runner and use stainless steel components in the construction of that hot runner to withstand those corrosive effects. And when it comes to high temperature applications, so one more thing, the stainless steel construction of hot runners and their components for corrosive applications is not meant to make that hot runner corrosion proof, because stainless steel only resists corrosion. So that means that those corrosive effects will also long-term affect the stainless steel parts. So they will also degrade in performance and structure. It's just that they are more resistant or more strong against that. When it comes to high temperature applications, we also have a lot of very good experience. We will build those hot runners in a certain way to help to withstand some of those high temperatures, just because increased temperature typically decreases strength. So we want to make sure that the hot runner can withstand or work with those high temperatures. And when it comes to hot runners that use valve gates, that is something that we sometimes have special construction guidelines on to work with those applications. We will often do other things. We will often make recommendations for specific mold cooling or specific plate cooling or specific processes in order to manage not just the processing, but the startup and the shutdown of those hot runners.
So how many cycles can a hot runner run without any type of system maintenance?
That really
How many?
depends. How many cycles?
Yeah.
That depends on the type of hot runner. So the type of shutoff that's used. Is it a thermal gate? Is it a valve gate? It can depend also on the material that's molded. So it can, if it's a polyethylene, if it's a PET, if it's a polycarbonate, for example. And it also depends on how that hot runner is operated and maintained along the way. One of the things I always recommend is, let me see here. Now I say everything depends. You should be able to get probably 3 to 5 million cycles out of nearly anything that you have. But it also depends on the components. If you have a valve gate system, some of those O-rings or some of those pneumatic seals can wear more quickly as plate temperature increases, as cycle time increases. But other things can be expected to last for a very, very, very long time. Of course, if you have a glass filler in the material, that can wear out components very quickly too. So it's not a satisfying answer because it's not always the same thing in our industry. In plastics, there are a few thousand different ways to accomplish the same thing. A part designer is different from each place. A mold designer does it more differently, and if you take a mold, the same mold, to 10 different processors, they will each process it differently and usually still be successful. So yeah, just like a vehicle or a motorcycle or a scooter, the same one can go through many different things and probably see very different results, just depending on how it's taken care of through its lifetime and along the way.
What are the quality improvements that we can expect from ULTRASHOT compared to a traditional melt delivery system?
ULTRASHOT is a very special kind of system. So it's, I recognize that we are talking about hot runners, which is a melt delivery system. That's how we get for the molten plastic from the machine barrel to the cavity. But ULTRASHOT is also a melt delivery system, but it is also a fill control system. So one of the things that makes it better, or to do, as you said, bring improvements, is it uses its own controller to control the fill of the cavity. And what it can do is it is using, therefore it's not limited by the capability and the maintenance of the injection molding machine. The fill control and the fill plungers are much closer to the cavity. That means there is much less melt between the cavity and the fill control. That means the control is much less degraded. This is really best used for very small parts, not for big parts, because the fill control of an injection molding machine is typically good enough to make that happen. But it's really best for small parts because of those very tight and specific controls so close to the cavity.
Any hot runners for PEEK material? PEEK?
Yeah, is that the polyether ether ketone? Yes, Husky builds several hot runners for PEEK, so PEEK and PEAK. We build several of those a year. Those are not applications that we are unfamiliar with. We have experience with those materials. We will, of course, the best way to talk about those is to contact a Husky area sales manager who should bring a technical expert like a Husky application engineer to talk about those applications specifically. But to keep it quick and to let other people ask their questions. But we are very familiar with those materials. We're very familiar with what those need. We recognize that a lot of those applications are considered high temperature, where you need a very high melt temperature. You also need a very high mold temperature, and because of that, you will need either an oil cooler or a steam thermolator to control that mold temperature. So, but we have other special components to work for PEEK, and we have other recommendations. So the Husky application engineer will be the best person to talk about it for more than 5 minutes, like me.
Can you give specific examples of how hot runner technology has impacted part quality?
I would say we very rarely see scenarios or applications where it is a one-to-one change. When I say that, we don't see a system that goes from 4 cavities to 4 drops or 8 cavities to 8 drops. We will typically see somebody go from a small number of pure cold runner, like a prototype mold, and then they will go to a high cavitation hot runner. But some of the impacts that we have seen in some of those conversions is the gate relocation and the elimination of the cold runner really helps really helps the molder to use a cooler melt or a lower melt temperature. The advantages of that are typically less warpage, just because now the melt temperature is lower, so the time to get from melt temperature to ejection temperature is reduced. That also helps to give a faster cycle time. Also, because that cold runner is removed, now the cycle time is also faster. You don't need to freeze as much material in the same amount of time. And there is typically higher output, not just because of higher cavitation, but because you are able to achieve a faster cycle time. Also, that the hot runner allows for more tuning and more adjustability. So one of the things I always explain is there are 5 components to an overall manufacturing or injection molding system. There's the resin handling, there is the resin itself, there is the melt control or the injection barrel, there's the clamp unit or the platens that control the opening and close speed as well as tonnage. And there is the mold and ejection. And finally, there is the melt delivery or the hot runner. Out of all of those systems, there are very few things which you can change, and then you can change it back to its previous state in 5 minutes or less. And that really comes from the hot runner when it comes to temperature change and temperature control. So the hot runner allows for a lot of investigation and a lot of testing when it comes to making changes and working with the variation that comes with any injection molding process.
When would we want to when we want to look at an ultramelt system versus a standard HR system?
An ultramelt is really best for materials that are very sensitive to temperature, like a polycarbonate. Also, a material that's very sensitive to chemistry or to the chemical reaction that might take place with a standard hot runner steel construction, like a polycarbonate. So I would say ultramelt is really best geared or best focused on polycarbonate applications first. I would also say it will be very good also for applications that are considered or known to be corrosive, a lot like a lot of the bioresins that are becoming very popular globally right now, PLA and PHA, and some of those materials which have corrosive additives like halogenated or brominated flame retardants.
How to solve the flashing issue for a valve gate?
I know I talked about that a little earlier, I think maybe in the middle of the presentation, and we probably won't solve a valve gate flash issue on this call. So I would encourage the person who asked if they have an issue, first of all, to contact our help desk, and we can work with you on your specific issue. But as a way to prepare for that call, it's always good to have the full process information, and also to have good measurements of the gates. And that's really to put the gates through a CMM and to measure not just the gate diameter. I don't recommend to check gate diameter with gauge pins, because that only tells you what's the largest pin you can push through a gate. It's really about finding the profile of the gate. So I always recommend having information about each gate, where you measure 30 points. Well, you measure 3 planes and you measure 30 points on each plane when checking your gates with your valve gates with a CMM. That's very good information to have, just because then that can also be compared with the process to see what's going on. Also, it helps to adjust some process conditions, not as a way to fix it, but as a way to investigate. So it's always good to try processing with reduced hold time, reduced melt temperatures, or reduced mold temperatures, to see and to know the effect of those settings on that flash also.
How do the hot runners control the acetaldehyde in preforms, and also how the melt material reaches in temperature at the same melt temperature? This is a question from our audience.
That sounds like a preform question, and
Yes.
And unfortunately, unfortunately, I myself don't work with preforms that much. I know that that material is or that aldehyde is a result of some of the chemistry of PET, and that's a very common thing to work with when processing preforms. But I would encourage that person to reach out to either our help desk or to a Husky salesperson to line them up with one of our experts to help them to work with understanding that better, because we build so many PET preform systems out there. We can definitely put that person in touch with an expert to help them discuss that question and learn more about that aspect of preform manufacturing.
Okay, so we have one final question. Are there modifications and hot runners required for the molding of recycled PET?
That's probably also a good preform style question, just because rPET is becoming more and more popular, preforms and preform manufacturing, but we are also seeing this happen in other hot runners where people are, or where molders are more and more interested in molding with PCR or post-consumer recycled materials. The short answer is no. We don't expect modifications to a hot runner in order to mold recycled material. One of the things to remember is that with recycled material, the material has more heat history to it, and there is more inherent variation in that material, in the feedstocks and in its molecular weight distribution. So there is a lot more variation in the properties of that material, and there is a lot more variation in the melt properties of that material. So it's good to, or it's really important to understand, even though all of the control for the processing is very tightly controlled, your melt delivery in your hot runner temperature control, your machine control, your mold, that is always going to be the same and very consistent. But the properties of the melt as it's processing from the hopper to the cavity is going to have some inconsistency, or it will have more variation. So it's also important to understand that there may be some variation in the manufacturing process itself. That means maybe a little more warpage, a little more scrap. One of the other things that sometimes happens with recycled material, with PCR, is there is a greater risk of contamination, and that's real melt contamination. So there can be metal chips or wood splinters in the material. A valve gate is typically a bit better for processing those materials because the gates are larger and they can allow that contamination to flow through the gates once that contamination gets from the machine through the melt delivery system and to the gate, and through the gate to the cavity. That will at least help to push that through and prevent that from being caught in the tight restriction that can be a thermal gate.
Thank you very much, Derek, for patiently answering all those questions. Thank you very much to everyone. And with this, we conclude our webinar. And I would like to thank Derek, first of all, who is right now wide awake. Very early morning, he has logged in to present us with this and to answer our questions. Thank you for sharing your experience and for this insightful session. Additionally, the thought-provoking questions from the audience made the discussion very lively. We hope it was a learning experience for each stakeholders of the summit. Derek, you were saying something.
I was just agreeing that the thought-provoking questions were very helpful to make this webinar much more engaging and much more lively, more exciting. And I just want to thank you for managing this today. Thank you for hosting this. Thank you to everybody who was watching. Thank you for your time. Thank you for your attention. Thank you for your questions.
Thank you, and have a very good evening.